Hi, I'm Tim, and this is the second video of the series. This one's dealing with elliptical galaxies and galaxy clusters, and for both of those subjects we quite quickly get on to some actual evidence for the existence of anti-gravity matter. So this is a slide from the first video, and the important thing here is that the total acceleration of gravity and the attraction of the AGM lacuna is gm over r squared and then 1 plus an squared over GAA. If G equals an equals AA, then the contents of the bracket equal 2. So from that we would expect that the effect of the anti-gravity matter atmosphere is to apparently double the mass of a normal matter object. So elliptical galaxies are normal matter objects within an anti-gravity matter atmosphere, and from that we would expect that their apparent gravity would be approximately twice what would be expected from the visible mass. We would also expect that that apparent extra mass would be closely located with the visible mass. We wouldn't expect there to be an apparent dark matter halo in the space around the outside of the galaxy. So this result has been produced by measuring the characteristics of several Einstein crosses around elliptical galaxies. And the researchers here have measured the characteristics of the Einstein crosses and estimated the apparent mass of the galaxies, and what they find is a mass to light ratio of about 1.8, and they say also not more than 2. And they also say that the mass distribution closely follows the light distribution and does not show evidence for an extended dark matter halo. So that fits quite nicely the prediction of the anti-gravity matter theory. On to galaxy clusters. Here's a picture of a galaxy cluster. Within the cluster there are many galaxies. They are all moving chaotically, falling inwards, interacting with each other, flying outwards again. In the space between the galaxies, of course, is anti-gravity matter. And the anti-gravity matter is being pushed out of the way at high speed by the passing galaxies, and it is heated up. And it's actually heated up to very high temperature. Anti-gravity matter doesn't like to change from the background density, but if you heat it up to a very high temperature, you can get a small reduction in density. The density reduction is small, but the volume of space is enormous, so it adds up to a significant effect. So that's what's portrayed here. We've got radius measured from the center of a galaxy cluster. Within the region of the galaxy cluster we've got a slight reduction in the density of anti-gravity matter. And we refer to this lacuna as being a dynamic AGM lacuna because it's caused by movement of the anti-gravity matter or temperature of the anti-gravity matter rather than being caused by a normal matter object. Now if you measured this perhaps by micro-lensing and then interpreted the effect as being caused by dark matter, you might come up with that kind of result. The apparent dark matter curve is actually the inverse of the anti-gravity matter density reduction curve. But that shape of anti-gravity matter density profile can't be the whole story. An anti-gravity matter particle that's way over on the right, a long way away from the cluster, wouldn't be affected by the high temperature and would feel an attraction to the AGM lacuna, and it would want to move to the left. What actually happens is this. The anti-gravity matter that's displaced by the galaxy cluster actually piles up around the outside of the cluster in what we call an anti-halo. That is to say, a region of increased density anti-gravity matter. And then outside the anti-halo, it falls back down to the background density DAB. Now, for a particle that's a long way away, the attraction to the AGM lacuna is cancelled out by a repulsion from the anti-halo. However, if you interpret this as being caused by dark matter, you now find that there's a region of apparent negative density dark matter, which is difficult to explain. So here is the bullet cluster, and the researchers here have done that kind of analysis, and they've plotted contours of mass density. So we can see that the highest peak of mass density is just to the left of centre, and then to the right of centre there's another lower peak of mass density. But also on this image we can see dotted line contours, and these are contours of apparent negative density. The researchers explain this by saying that the mass density has been zeroed at the edge of the image. But that's not a complete explanation, because we then have to explain why there is dark matter at the edge of the image, and then the dark matter density seems to reduce as you come in towards the centre, and then it goes up again as you get closer to the centre. This is another cluster, Abel 1689. And what's plotted here is mass within a circle as seen from the Earth. So when the circle is small, the mass in the circle is small. As the circle gets bigger, the mass in the circle gets bigger, until you get up to about 3 arc minutes. And then, as the circle gets bigger, the mass in the circle gets smaller. So both these galaxy clusters show evidence of an apparent negative mass density around the outside of the cluster, and that is as is predicted by the anti-gravity matter theory. So I'm going to stop there and return to my collection of AGM terminology, and the terminology that we've added is the dynamic AGM lacuna, which is an AGM lacuna caused by dynamic effects or heating, as opposed to a static AGM lacuna caused by gravity, and an antihalo, a region of anti-gravity matter with a higher density than DAB, usually around the outside of a dynamic AGM lacuna.